suggests that there is material from Earth that is actually on the moon. And that's important because it preserves the history of Earth. The moon, unlike Earth, has no air, no water, and no magnetic field. And this means what happens when you leave a footprint there, the footprint remains. So that's very important. So the story of Earth, early story of Earth, unlike Earth where you have all these tectonic activities, all these things actually would really wash away a lot of the early signatures of these things. So the moon preserves this information regarding what happened to, what was the environment early Earth actually formed. And clearly early Earth, life didn't come on Earth until very recently compared to the 4.6 billion years, and partly that could be because of the fact that it was a very violent place to live in. Collisions of all types happening all the time, where they didn't allow life to even sustain. So the rate of collisions, kind of a material that actually collided, all that information is seen in the craters of the moon, in the debris around the craters, and that's the story we really like to read around. So there's a clear reason for us to study the moon, to study Earth, to know about Earth itself. And of course, as I said, once we know there's something out there, we really would like to learn and explore. That's what makes humans humans. And the possibility, as I mentioned earlier, for as a resource for future exploration of the solar system. So after the initial phase, I already mentioned some of these things, that you see there is no atmosphere, which means no erosion on the moon, no plate tectonics, surface which is driven by impact cratering, and it's a crust. Primarily, what you see is a lot of powder at the level of, maybe it's about a meter or more, depending on the location. And one of the biggest worries when Apollo astronauts are landing is how much will that Eagle lander sink? It is a real concern, and fortunately it didn't sink too much. And but there is still, the powder is still very fine, and this powdering happens because, unlike Earth, which has an atmosphere and a magnetic field, absence of these actually means the cosmic meteorites. There's a lot of smaller particles that are constantly blowing away in the solar system environments. They're all impacting the surface of the moon, and on the rocks, they break rocks into smaller and smaller pieces. This has been going on for millions and millions of years. That leads to like a fine gravel at the level of microns, tens of microns. You see a distribution of these, and forms this powdery surface in which you see pictures of astronauts going around, and, their body covered with these things. And tomorrow, for a human's presence on the moon, one of the biggest challenges is going to be this lunar dust. This dust that exists from these things. It's sticky, electrostatically it seems to really stick to things, etc. So these were our concerns when we were also designing a rover and lander. What will happen to this lunar dust as it actually blows away? There was an interesting experiment. One of the Apollo missions landed very close to the Explorer 3 spacecraft, an autonomous spacecraft that landed on the moon many years ago, and they landed within 200 meters of this. And the landing produced such a huge blowout of this dust. They went and saw, astronauts went there and picked up some material, they brought it back. They looked like they were sand-blasted. And they were sand-blasted from the landing of that Apollo mission. So this dust is a serious concern. But end of the day, we will find ways to manage it. And you then look at this, look at the surface of the moon. It's primarily made of material that's very similar to what's on Earth. They have these the minerals of olivine, pyroxene, feldspar, which sometimes also called anorthosite, and so on. So when we made a lunar test terrain facility in Bangalore at the ISRO Satellite Center, we were looking for the right anorthosite, because a lot of the moon is made of anorthosite. And anorthosite itself, or when you look at the mineralogy, it comes in various grades. There's an AN number attached to it. But it turns out one of the cleanest, and anorthosite resembles the lunar anorthosite very much, is something that happens in a place near Salem, a place called Sitambuldi. And we went there and got these rocks pulverized into many grades that are very similar to the soil levels that we have. Mixed them up. We have a test terrain facility at ISAC. It was put up almost 10 years ago, and Periyar University was very helpful in getting these things going. So we created such an environment, but the material is largely not very different from what we on Earth, because again, going back to the giant impact theory, that's not a big surprise. It's stuff that we have here that is really out there.
But if the material is very similar to Earth, why we do not have any sign of magnetic field?
Magnetic field is different. Magnetic field comes from the core. So that is the real issue. If the core doesn't have molten core, iron dominated, with a dynamo that sustains it. It may not. So that is the interior of the moon is what we do the least today. There is some evidence of it, the fact that there is a small core, but the liquid core nature of it is not understood. So what it believes is it's probably not there. When we look at Venus, we have a similar issue. Maybe it doesn't have a liquid core that can sustain a dynamo. So whatever limited magnetic field we see is fields coming through the solar wind. The sun's interaction leads to small scale fields, but nothing at the global scale. All right. So now, it's also, there seems to be evidence from the Apollo samples that when you look carefully, you can see there was a time after the formation of the moon where there was massive melting of the surface. And that melting is what is now being called the late heavy bombardment phase. Around 3.9 billion years ago, it is believed that something caused much greater occurrence of bombardment of material on the surface of the moon, and so much of it such that it actually melted, formed largely a molten surface from which it cooled. So which is what is called the late heavy bombardment. And the evidence of that comes actually from studying the rock samples that we have. And it's possible because of the fact that the solar system as we see today is not what it was necessarily. The big objects like Jupiter and Saturn could have moved, and there are a lot of evidence to suggest they moved. When they move, it's like, gravity tells us every body interacts with each other, and the big ones move, others move, small ones move, and once again we have this massive collision that can actually happen. And so believed in 3.9 billion years, such an event led to this heavy bombardment when much of it melted, formed rather like a magma ocean, in which crystallization of materials happened. The heavy ones sank, the middle ones, the early ones remained here, at the top you have a lot of anorthosite at the top. So that's what you now see as the moon. And when this melting happened, the craters that were previous earlier were filled in by this matter, and that is what we see as these dark regions called mares on the moon. So that's the current understanding of how the moon looks like. Now, if we want to study this, the moon as an object, we want to really understand the composition. The composition can be in chemistry. You take anything here, I'd like to know the composition of this stuff, but it's also important to understand the mineralogy of this stuff, the formation of crystals. It tells you the history of how these things formed, where it came from, and so on. So when you do both chemistry and minerals, you can do fluorescence, X-ray fluorescence to derive abundance issues, but if you do X-ray diffraction, you can understand crystalline structure of it. And so there are ways to really do that. You study volatiles because of the low gravity on the moon. Many things escape. I mean, anything, if you have, say, argon deep in your crust, it actually escapes. There is hydrogen and helium that was there earlier. The lighter elements will escape faster, depending on the gravity of the body. But studying the rate of escape of volatiles is very important. Study the subsurface for looking for things like water. The exosphere is this very thin, limited atmosphere, very, very thin atmosphere, where basically the mean free path becomes very large, the collisions are not there, and that is what we can study from about 100 kilometers. And the sun, of course, solar wind interacts with the surface, and then of course the interior, which means you really look for quakes and see it is active, seismology on the moon, and then there are interesting things about the moon is not a perfect sphere, variations, and then so there was a very interesting mission by NASA that actually had 2 satellites which would move like point objects around the moon in an orbit, but these orbits will be slightly perturbed every time there is gravity anomalies. And so they look at the relative difference between these two, and beautifully called GRAIL. It's a fantastic instrument measurement, very differential measurement that actually do very well the structure of the moon, the gravitational potential of the moon. Now this is very, very important when you want to land or do anything else there, because typically a satellite 100 kilometers undergoes perturbations because of the non-sphericity of the stuff. These perturbations, if you don't correct with fuel on board, will lead to, in 6 months, the craft could actually crash on the surface of the moon. But the knowledge of the potential deviations allows us to model this very precisely and control the spacecraft. And your landing, very important. So that's why it's very important. And today we have very good models. Great. So these studies of the moon, you can actually do it from ground itself, from Earth itself. You don't have to go there to do it. Today, big telescopes can actually do that. And so there are things that we do from Earth and from Earth's orbit. Satellites in Earth's orbit, the Hubble Space Telescope looks at the Chandra X-rays Observatory looks at the moon. You can actually study this. And you can see spectrum. You can look at the abundance of oxygen in that. But it doesn't tell you the resolution that you want. Where is it? Which is a good place. I want to do titanium mining sometime in the future, which is the right place to go for that. That you really need orbiters around the moon. And oh, sorry, I didn't need the nonsense there. That means without the human in the loop, okay, landers, rovers, etc. will all be required. Otherwise, of course, you bring your sample. The sample has this enormous value that you can bring it to a lab, do this, use these very powerful instruments that today have to really study a lot about this. So bringing back sample is a very, very important thing. Some was done, the Russians, the Soviets at that time did this autonomously with their lunar missions, where they would automatically bring back some samples. So those exist. We have a little bit of sample at the Physical Research Laboratory given by the Russians in one of the lunar missions. It's sitting in some cupboard somewhere. A lot of work has been done on it, but it's still preserved and carefully. Americans brought a lot of it. And I said they're being very stingy with it. They're only giving it out in the form of trickle. But what is amazing is that that trickle that has been given out itself has produced such an incredible array of results regarding the moon and various things. So bringing back sample is absolutely critical. I mean, today, thinking about having a mission to Venus, one of the key things I would really like to have done is to really go there, get a bit of that air sample at 70 kilometers and bring it back here for exactly this kind of work. Because what you can do with the laboratory on Earth is many, many orders better than what you can do with an automated, machinery that can actually study these things. So bringing back samples are very critical. So there will be new missions to bring back samples from the moon, bring back samples from Mars, which is in the nearly towards 2030, but missions will start going to 2024 onwards. So that's a very important thing. So there is a lot of ways to study the moon, but samples do play a very, very important role. Now this is a picture that shows all these blue dots are, I think, where the Apollo landed. Red dots are where the Soviet Union had their automated systems, and many of them also carried these retroreflectors, mirrors that have from air, whichever direction you shine a light in, it will reflect back in the same direction. A plane mirror doesn't do that, so you have these what are called corner cubes, like what you have in reflectors today. So they are